Hello, once again, and welcome to lesson 4. In lesson 3, we left off where we've just created our first project, and then I was explaining to you and describing to you the main OB1 programming block. And we've said that this main OB1 block is a block that is cyclically executed by the CPU. So if there's a function that you're going to add onto your program, that function must be called on the main OB1 for execution. All right. So in this lesson, I'm having a short presentation of the exercise that we're going to be writing a program about. Okay, so I've already opened the software since I assume you know now how to do that. So we are on the existing project, open existing project. I'm going to open the first project, which is the project that we created. As you can see, it is opening. We're opening a project. Then after we've opened the project, we're going to go to main OB1. That's where we're going to do our programming on the main OB1 for now. Okay, I want us to write a PLC program. Then I want to open the main OB1. So here I want us to be writing a program. We will keep on adding the next. So it is the first network. But before we do that, I just want us to go and understand what is it that we're going to do on this short presentation. Okay, I'm going to go and click here on lesson 4. Then we started presentation. So this is lesson 4, and this is the exercise, the programming exercise. So the first instruction will be motor B cannot be started unless motor A is running. So this is a sequence. Okay, so we're having two motors, motor A and motor B. If we want, we can assume that we're having two conveyors, conveyor A and conveyor B. Okay, but conveyor B cannot be able to run unless conveyor A is running already. Okay, condition number 2, motor A and motor B have their individual start and stop push buttons. So each conveyor will have its own start and stop push button or push buttons. Okay, so motor A has its own start and stop buttons. Motor B has its own start and stop push buttons. Okay. Condition number 3, motor A and motor B have their individual isolators. Both motors will not run unless these isolators are in the on position. Remember, an isolator is an on-off switch. This isolator is a type of isolator that is, we can say, is a triple pole isolator having an auxiliary normal open that is wired in the control circuit, such that if the isolator is in the on position, this normal open contact will change to a normally closed contact. If you put it back in the off position, this normal open contact, normally closed contact will change to a normally open contact. Okay, disabling the motor. All right, so we have these 3 conditions. And also we mustn't forget that what we are controlling here, we are controlling motors. These motors are 3-phase induction motors, if I may say. So we are not looking onto the power circuit, we are looking only in the control circuit. That's what we're going to be writing on our software. But this particular software, this particular instructions that will be written on the software are telling the PLC what to do. Is the instructions. The CPU is going to execute those instructions, and then it's going to update the outputs. Okay, remember, this is how the PLC works. We've got inputs and outputs. In the middle, we've got memory, and we've got the CPU, which is the brain of the PLC. So before it goes onto the CPU, there's something which is called the PII. The PII must be updated, okay, of the inputs, in this case of the start and stop instructions, whether it's 0 or whether it's 1. And then when that is being updated, it's going to now create an image which is going to be looked at by the CPU. And then the CPU is going to execute the instructions based on the PII. After that, when the program has been executed, the PIQ is going to be updated, telling the outputs whether the output is going to come on, or it's going to be off, or it's going to be high, or it's going to be low. Remember, in this case, if we were to wire a PLC panel, we will be having, say, relays for outputs. These relays will be wired in such a way that they activate the contactor for these motors, so that if the relay is getting a 24 volts, it's going to energize and then activate the contactor, which is now wired on the PLC panel. All right, but now depending again whether how do you want to wire it, because it's looking at the standards and how you want to wire it. Okay, but remember, we are looking, assume a 24 volts PLC, in this case VDC, and then even the inputs to the PLC are 24 volts, even the output is also 24 volts. Okay, but the relay itself must be able to handle the contacts of the relay. They should be able to handle, say, I don't want to say high voltage. They must be able to handle 230, 380 volts AC. I'm not sure whether you're following this. So I'm gonna be posting a video on also hardwiring, and then you can understand how the PLC is wired, the PLC panel, just basic hardwiring. Okay, then you get to understand. But what is actually happening here, we are having in the PLC panel, we are getting power to the panel, then we're having a transformer, and then we're also having, say, a power supply. This power supply is giving us 24 volts. That is what we're going to use on our control circuit. And we also want to use 24 volts to energize the CPU, which is the controller, which is the PLC. And also, inside the PLC, inside the controller does not use 24 volts. Remember, the card gets 24 volts high or low, on or off, 24 volts or no 24 volts. But what is the voltage inside the small components, inside the electronics of the PLC? Is less than 24 volts, which is, say, about 5 volts. Okay, are you with me? So in the input card, in the input module takes 24 volts, but the CPU looks at 5 volts. It is actually executing those instructions as 5 volts, which equates to 1 or 0. Okay, without any waste of time, let's recap on this particular exercise, because I've said a lot of things now. So we've got two motors, motor A and motor B. Motor B cannot be started unless motor A is running. Both motors have their individual start and stop push buttons, and then both motors have their own isolators. isolator B and isolator A. And then these isolators will control the motor, whether the motor is going to run or it won't run. So it will only run if these isolators are in the on position. Okay, don't want to waste your time. Next instruction. In this exercise, we will not consider overload settings and motor temperature. Okay, we're going to leave that out for now. I just want us now to go and step by step write a small program on main OB1 based on these instructions. Okay. All right. So now what I'm going to do, I'm going to open again the TIA portal. Now this is the program editor. That's where we're sitting now. We are actually here. So I assume you guys have a little bit of electronics, and also some of you are electricians, some of you are engineers, some of you are technicians. So you'll actually understand the basic contacts, the basic relay, and the timers and everything. I hope, if you feel you need more explanation, I will also make a short video on those things. Okay. So the first network, we're gonna be starting motor A on the first network. But before we do that, I want us to update our PLC tags. I always recommend that just fill in your PLC tag table all the time before you start any program. It will make your life easy. Okay, so we go to PLC tags. Let's add a new tag table. Okay, let's just add a new tag table. My computer is a bit slow, so this is our tag table. Tag table 0. I just want us to rename this tag table. Let's give it a name. Let's say motor. Like that. Motor. Say sequence. Something like this. Motor sequence. Okay, so this is our tag table. Then we're going to open the tag table. Then we're going to start filling the inputs and outputs on the tag table. Okay, so that when we start writing a program, we don't have to keep on typing. It will just pop up all the time. So the first one, let's say, the first, for instance, let's say the first input will be the start button for motor A. So let me just say start. Start, say MA. And then data type is bool. Data type is boolean. It's either true or it's false. It's either 1 or a 0. It's a start button. It's a normal open contact in this case, because the start button is a start push button. It's not a toggle switch, but it's a push button. Okay, so they gave us a default address there as i0.1. Okay, we can change that. Let's change it to i0.0 in this case. Not a problem. Let's put i0.0. So this is our okay. They say it's been, so in the same, it's already been used somewhere. Let's put i0.0. It's not a problem. Let's put i0.1. Okay, which is correct. It's fine. Let's leave it at i0.1 because it looks like it's been used somewhere in the program. It's not a problem. And then the next one will be stop. Say stop motor A. It's i0.2. It's also bool. The next one will be, say, the isolator part. The isolator, let's go ISO say motor A. Let's give it, it's also bool, is i0.3. Okay, so we have 3 inputs for motor A. We also gonna have 3 inputs for motor B. Okay, so we're gonna have start, MB is gonna be I 0.4. Stop MB is gonna be I 0.5. And then we also need an isolator, ISO MB. Okay, that is going to be I 0.6. All right. So start MA, stop MA, ISO MA, start MB, stop MB, ISO MB. So this is start button for motor A, stop button for motor A, isolator for motor A, start button for motor B, stop button for motor B, isolator for motor B. Then we're going to look at the outputs. How many outputs are we having? We're having 2 motors, so we're having 2 outputs. We can add indicator lights, but for now, let's not add indicator lights. Don't do that. Okay, we're going to just put 2 motors. Okay, so this is the actual motor. What am I doing now? Motor, say A. And then there's an output. It's not an input. Okay, it's an output, so it's actually Q. Just put 0.1 also. It's not a problem. So this is motor A. And then motor B will be Q 0.2. So this is your tag table for this motor sequence. Okay, so what we're gonna do now, we're gonna save. Okay, once we've done that, then we can close our tag table. Then you can start programming. You can start programming from now on. So on this network, we're gonna type in start motor A. Okay, start motor A, that's what we are doing. Or we can type in motor A control. Okay, I think that is proper. That's fine, not a problem. So let's start. So we need a normally open for a start button. We're going to use a normally closed for a stop button. We're going to use a normal open for that isolator. Then we're going to drag and drop the coil for that motor. Okay, so we open our bit logic operations there. What I'm going to do, I'm going to drag and drop the normally close push button. Then I'm going to drag and drop the normal open push button. Then I'm going to drag and drop the second normal open push button. Then I'm going to drag and drop the coil there. Okay. Now, this is going to be my stop push button. This is going to be my normal open start push button. This is going to be my normal open isolator for motor A. But as it is for this arrangement, because these are push buttons, so if I were to press this button here, this motor will start running, but it won't latch, it won't retain itself. So I need to create or design a retaining branch. Okay, which is going to be across here. Are you with me? Okay, so I need that retaining branch there. Drag and drop. We can just double click there, it's not a problem. We can double click, it will go there. Then we can just pull this and connect here. Okay, we're learning a lot now. So here we are now. Then you can start now. You can see on all these contacts, we are having question marks there, and it tells us the network is actually crossed red there. It tells us that there's something wrong. We are not done. There's an error because there are no addresses on our network. So we need to put the addresses on our network, on our instructions. Okay. So the first one is a stop push button. So because already we've got text on our tag table, you just type in stop. See, it pulls up stop MA, just what you want. Pull stop MA. That's what you want. Are you with me? So there it is. Then this one, we know this one is actually start MA. There it is. You select that one. We know this one is ISO. This one is ISO MA, isolator for motor A. We know this one is our motor A. There you go. And then we can now retain, because this contact belongs there. Are you with me? So that when the motor is running, this branch will be active, retaining power there. Are you with me? But this is a push button. A push button is spring-loaded. So when you press that button, power will flow, current will flow. As soon as you remove your finger, there is no current. So you need to latch that branch, that circuit. Okay, as you can see there. So this is actually, it will have the same address. It will have the same address, which is MA, such that when this is active, that one is also active, because this contact belongs there, having same addresses M, motor A, Q0.1, Q0.1. Remember, I is for inputs, Q is for outputs in the Siemens environment. Okay. And then this type of addressing where we are saying is I0.1, it tells us that I is for inputs, 0 is for the byte. Okay. And then 2 will be your bit. So we call this, let's call it bit byte addressing. Let me put it like that. Or byte, let me call it byte bit addressing. I think it's proper like that, because the first one is the byte, then the second one after that comma is a bit. So it's telling me that this particular stop button is wired on 0 byte, bit number 2. The start button is wired on byte 0, but bit 1. Are you with me? The isolator is wired on byte 0, bit 3. The output, which is the motor, which is the relay in this case, is wired on byte 0, bit 1. Are you with me? Okay. So we've just designed the first network where we can start and stop motor A. Now let's go on to network 2, where we're going to be designing a circuit without forgetting the condition that motor B cannot be started unless motor A is running. As it is now, if this is active, motor A will be running. So what is it that we need from motor A to make sure that, or to prevent, or to allow motor A from running? Because we want a condition from A to allow this motor to run if motor A is running. Okay, that is on the circuit. So this is what we're going to do. But at the same time, we mustn't forget that we haven't said anything about whether if motor A stops, what's going to happen. That condition is not there. We mustn't confuse the two. we want both motors to stop individually. Okay, so let's design. So we're gonna drag and drop again the normally closed push button for motor A. For motor B, we're gonna drag and drop the start push button. We're gonna drag and drop that isolator. No, not there. Sorry. Let's go undo. We can do that. We're gonna drag and drop. It doesn't want to go there. Why? Let's just double click on it. It should go there. You can also double click on the code. You'll go there immediately. Okay, there you go. Again, we must not forget that we still is the same scenario, but we need to retain that branch. Okay, so retain the branch and put the normal open contact there. Also pull and put it there. As it is now, it is the same circuit. Okay, I just want to put all the addresses before I put that condition. Okay, so this one will be a stop button for B. This one will be a start button. Start button for B. This one will be an isolator. An isolator for B. This one will be motor B. And also that one is motor B. Okay, are you with me? Now, as it is now, you can start and stop this motor without relying on motor A as it is now. Now we need a condition that is going to prevent this motor from running if motor A is not running as yet. I hope I'm making sense. Okay, so network 2, we can put a comment there. We can type in there, say, let's type in motor B control, something like that. Okay, now we can take a normal open from motor A and place it, say, somewhere here. Are you with me? Such that even if you start motor B, it won't be able to start unless that normal open. Let me just drag and drop the normal open and put it somewhere here. Okay, you can do that. We can take a normal open from motor A and put it there, somewhere here, such that if this is not active, you won't be able to start motor B. Are you with me? But now ask yourself a question. What is going to happen if I were to stop motor A before motor B? Guess what's going to happen? Motor B will also stop with motor A. Do you want that to happen? Think about it. No, you don't want that. So think carefully where you want to place this normal open contact. It does not belong there. Okay, so we're going to delete that. What about placing it somewhere here? Okay, let me place it there. This is MA. So if this contact is sitting somewhere here, if I were to start this motor, it won't be able to start unless this is active. Are you with me? Unless this is active, unless this motor is running, unless it's active. Then the motor 2 will be able, or motor B will be able to start running. Then it will return itself there. So putting it or placing it somewhere here will also help, because even if this motor is inactive, is not running, even if this motor has stopped running, are you with me? Or if you were to stop this motor, it won't stop motor B. Because what we want it to prevent it from starting, but it can stop on its own. But you cannot start it if this motor A is not running. But it mustn't stop with motor A if motor A is stopped. Are you with me? I hope I'm making sense. All right. So this is what we have now. So what we're going to do now, we're going to be saving a project. Then we're going to start playing around with the simulator. Okay. I think this project of ours is taking too long. I don't want to be posting long videos. Okay. Now let us start a simulator. We mustn't forget our addresses, because we're starting at I0.1. Mustn't forget that. Okay. Let's go there. So you just click on that simulator icon there, then wait for it to load. Then you can start simulating. Then you can download this onto the CPU. We can load the software onto the CPU. It's asking us a question. Starting simulation will disable all other interfaces, online interfaces. Do you want that? Yes, don't have a problem. Now this is my simulator as I explained it on the second video. There we go. Now this is what we want. As you can see there, we are having byte 0 there. Look at that card there. You can actually add academic close to those things, and then you can add, just add a card. Let's add. So let us insert an input variable. Is I byte 0 is bits from 0 to 7. It gives us 8 bits. Okay. As you can see, it wants us to actually download the program onto the simulated environment. Okay, it has compiled the program, and then there are no errors. So let us load that onto the CPU. Okay, this software is very clever and advanced. Okay, so here we are. This is our software. We've actually loaded this onto the CPU. I'm going to show you again. So this I byte 0 for inputs is actually is a visual card. Okay, 8-bit card. So let us add an output variable again, but in this case it's gonna be QB0. This is for outputs. Okay, and currently the CPU is on stop mode, as you can see there. So what I want us to do, I want us to put the CPU in run mode. Okay, let's put the CPU in run mode and see what happens. Now the CPU is in run mode and it's happy there, and you see even the SF LED is not red, even the DP for communication is not red. The DC is available, it's on run mode. You can see that. Okay, now I want us to monitor this program of ours. You click here for monitoring. Yeah, this exercise is taking a bit long, but it's fine. It's not a problem. I hope you guys will be able to actually download it from YouTube. Okay, there you go. So as as you can see here, already this, you see that stop push button there. Look at the stop push button there. See, because it's active already, it's a normally closed, that is also a normally closed, but both motors are not running. Are you with me? Both motors are not running. Now let us start motor A. The start push button is I0.1. Look into this. I0.0 is not active, but we're going to be activating I0.1, which is the second bit. Okay. Now let's activate it. So you're going to tick and untick because it's a push button. Let's tick and untick. Tick and untick. What's happening? Okay, so what's happening? Tick and untick. The motor is not running. Why this motor is not running? Ask yourself a question. There's a condition that said both motors will not run unless both isolators are in the on position. So make sure that both isolators are in the on position. Are you with me? So make sure that I0.3 is in the on position, and also I0.6 is in the on position. I0.6 is also in the on position. Can you see that? Okay. Such that now if you were to start motor A by activating start MA, which is I0.1 in this case, then this motor will start running. Now let's go back again and see, can this motor run? This motor will not run. Why? Let's see. So if we were to activate I0.4, which is start motor B, okay, let's activate I0.4 and see what happens. See, this motor is not running, so MP cannot run. MP cannot run. MP cannot run. Why? Because this condition has not been met. Are you with me? Now let's deactivate that. Unless MA is running, so let's start MA by activating I0.1. See now, so motor A is now running, and then even that motor A Q0.1 in the second network is active. Okay, are you with me? Now we can now start motor B by activating I0.4 there. Then this motor is now running. Are you with me? This motor is now running, and it has retained its self there. So even if I were to stop, let us stop motor A and see what happens by activating I0.2. Activating I0.2 will stop that motor, but it won't stop motor B from running. Are you with me? Let us now stop individually, stop motor B also by activating I0.5. Are you with me? There you go. Happy? So you can start and stop. You can start motor A, and then you'll be able to start motor B, but you should be able to stop both motors individually. Now let us start again and then see if these isolators are working also. So now if I were to activate MA and also activate MB, now if I deactivate isolator number 1, which is I0.3, it should be able to stop that motor from running also. Are you with me? And also I can stop that one with that isolator. Should be able to do that. I hope you guys have enjoyed this video, and I hope you